In this video, we're going to talk about unit vectors for motion. Let's start by talking about position. So for the vector for position, we actually use the letter r. So we would say that the length of this position vector, or its magnitude, is r. And it will have x and y components. Now you could say r sub x and r sub y, but because for position x is x and y is y, we just call the x component x and the y component y. Now, when we write about the vector in unit vector notation, we would say the vector r is equal to x, which would be my x component, I plus y, j. So an example with numbers would be, let's just pick some random ones. Let's say 3 and 2. We would say 3m I plus 2m j. So that would tell me that I'm located at an x position of 3 meters and a y position of 2 meters. Now, it gets kind of tedious writing out the unit that way for each of the components. So it's common for people in physics to put the unit on the outside and to use square brackets. 3i plus 2j. So to use square brackets for the whole vector and then put the unit on the outside, just like that. All right, now let's talk about the velocity vector. The velocity vector is a vector that we will call v, and it'll have a magnitude, v, where the length represents the velocity, and then an x and a y component. Now, for these x and y components, we are actually going to say v sub x and v sub y, because x and y are sort of reserved for position. Okay, so when we talk about the velocity vector then, we would say v equals vxi plus vyj. And whatever the x and y component of a velocity vector are, or is, sorry, that's what you'll put next to I and put next to j. Okay, so an example with numbers, we'll just randomly pick some. Let's say 10 meters a second. It shouldn't be r, it should be v. 10 meters a second I plus 5 meters a second j. Okay, so notice what's different is now my components are going to be velocities, so they have units of meters per second. And if I wanted to, I could use a square bracket and write 10i plus 5j and put the meter per second on the outside just like that. Now, if we've got position and we've got velocity, then we're also going to have acceleration. And acceleration will have the letter a for magnitude, then ax for the x component, and ay for the y component. Hopefully you see this pattern emerging. And for the a vector, the acceleration, we would say the x component of the acceleration times I plus the y component of the acceleration times j. And an example with numbers, I don't know, how about 2 meters per second squared I plus 14 meters per second squared j. If I wanted to write this a little more cleanly, I could say 2i plus 14j meters per second squared on the outside. Okay, so this is kind of how we write positions, velocities, and accelerations using our unit vector notation, so I, and the components that go next to them. Now, because you know the relationship for position, velocity, and acceleration in terms of derivatives, we can also write these vectors another way. So because we know some position vector is xi plus yj, we can say what the velocity is if we know what that x and that y component is, because we know that the derivative of position will give us velocity. So in this case, if I take the derivative of x with respect to time, I'll get the x component of velocity. And if I take the derivative of the y component with respect to time, I'll get the y component, or the j. So let's do an example. Let's say that you had an r, but instead of giving you actual coordinates, you had equations. Whoa. All right, well, that would look something like this. Let's say 3ti plus, how about negative 2t cubed plus t j. Okay, so if I had the equation written this way, I can quickly identify what the velocity vector is by simply taking the derivative of the x component with respect to time, which would be 3, so 3I, and then taking the derivative of the y component with respect to time, which would be negative 6t squared plus 1j. If I want to put that in parentheses, maybe that would help me. And of course, for both of these, I would need to put meters on the outside and meters per second to keep things organized. Okay, great. Well, maybe you can see what happens if we take the derivative one more time. If we do the derivative one more time, we'll get the acceleration. And again, that would be the derivative of x with respect to time, or the second derivative of position with respect to time. There should be a square there. So for us, if we wanted to find the acceleration vector, we would take the derivative of the x and the y. The derivative of 3 is just a constant, so that's 0. So I could write 0I. And then this would give me plus, let's see, negative 12t, and then the 1 would go away, j. Okay, so 0I plus negative 12tj meters per second squared. Although, honestly, if I was going to try and write as little as possible, I would write this, I would just not include the I, and I would write it negative 12t j meters per second squared. I might just simplify it, write it like that. Okay, so now that we have looked at this sort of organizational method for position, velocity, and acceleration, let's see what it's useful for, because it can make the problem-solving process for motion equations really simple and organized, since we've got all of the x motions in one spot and all of the y motions in another. Here's our example problem. You are programming a drone. The horizontal motion follows the equation x equals alpha t, and the vertical motion follows the equation y equals beta t squared plus 10 meters, where alpha is 2 meters per second and beta is negative 6 meters per second squared. Write the position, velocity, and acceleration vectors in unit vector notation. Then find the magnitude and direction of the position, velocity, and acceleration at 2 seconds. Okay, so let's start with A. Write the position, velocity, and acceleration vectors in unit vector notation, so I and j. Well, let's start by writing x and y in a bit more friendly equations. Math friendly, that is. So I would write x equals, instead of alpha t, I might just go ahead and say 2t. And the y equals, instead of beta t squared, negative 6t squared plus 10. Okay. Now, if I was going to write my position vector, I would write r equals 2ti plus negative 6t squared plus 10, j, and then close the bracket and put my unit m on the outside. Okay, great. Well, so now maybe you can see what the velocity and acceleration vectors are going to look like. The velocity is just going to be the derivative of the x and the y components, which if I write those over here, vx, that's just going to be 2, and then vy is going to be negative 12t. So this would be 2I plus negative 12t j. Close the whole thing in parentheses. And then the acceleration, a would be 0, ay would be negative 12. So I could write 0I, or just ignore it, and minus 12j meters per second squared for the acceleration vector. Okay, great. So that's the answer to part A. Now that I've written out these vectors, I'm actually going to just get rid of all this stuff right here and then move my vectors over so that I've got some room to work with them. So finding the answer to part B is going to be really easy because all I need to do is figure out what the I and the j component, or the x and the y component, is for position, velocity, and acceleration at 2 seconds. Then I can use my familiar magnitude and angle equations to figure out what these things are, so like for position, if you want to find the magnitude, x squared plus y squared, and the angle is tangent inverse of y over x. And it's the same for the velocity and the acceleration, only we're using the y and the x components of the velocities and the accelerations. So let's start. Let's start by finding the position vector at 2 seconds. Okay, so the way that I can say that I'm doing that is write r parentheses 2 seconds so when I plug into here to the time, and then here, I'm going to get 2 times 2, or 4i, plus negative 6 times 2 squared. Negative 6 times 4 is negative 24, plus 10 is negative 14, so minus 14j. Okay, so that's my position vector at 2 seconds. So to figure out what the magnitude of that is, I would say the square root of 4 squared plus negative 14 squared, which is going to give me 14.56. We'll say 14.6. And the angle is tangent inverse of y, which is negative 14, over the x, which is going to be 4, and tangent inverse of negative 14 over 4 is going to give me negative 74.05, we'll say 0.1 degrees. Now, because it's going to have if you got y and x, since it's going to have a positive x at 4 and a negative y at negative 14, then that means our position vector at 2 seconds is in the 4th quadrant, and therefore this negative angle is the correct unit circle angle. So that's great. Okay, so to figure out what the velocity at 2 seconds is, I just plug 2 into my velocity equation. So the I component doesn't change, it's just 2, so still 2. But this negative 12 times t, negative 12 times 2 seconds, is going to give me negative 24, so minus 24j, meters per second squared. Okay, so now I can find the magnitude of that velocity by doing the square root of 2 squared plus negative 24 squared, which the square root of 2 squared plus negative 24 squared is basically 24.08, so we'll say 24.1 meters per second, and then the angle for that would be tangent inverse of negative 24 over 2. Again, that's a negative y and a positive x, so it'll be in the 4th quadrant, and when we get a negative angle, it's going to be the correct unit circle angle. In this case, it's negative 85.23, so negative 85.2 degrees. Okay, so that's the magnitude and direction of the velocity vector. Now let's do the acceleration. If I want to do the acceleration at 2 seconds, then I plug in. Well, if you look at it, it doesn't depend on time because neither of those things has a t in it. It's just straight up, negative 12j. Now, what that means, if I was to graph, right, y and x, it has a 0 for the x value and a negative 12, so that's the acceleration. That means that this has a magnitude of 12, and the angle is negative 90 degrees because it's pointing down, exactly down. Okay, so that's the magnitude and the direction of the acceleration vector. Woohoo! You're doing so good. Now, let's pause here for a second and briefly discuss why do we use the letter R for position, and how can we get a picture of an object's motion if we know how its x positions change and its y positions, if we know how they both change. So just draw a y versus x graph, and let's mark a few positions. We'll call this R1. So there we go, R1. And then maybe this one is, that's a terrible R, R2. And then, I don't know, maybe sometime over here, you're at R3. You know what, these position vectors look like trash. There's R2. There's R3. So let's call this one R2, R3. Sorry, okay. So let's say you have these different position vectors. Each of these position vectors is going to have its own x and y coordinate, right? It's going to have like an x1, a y1, x2, y2, x3, y3. So we use the letter R because these positions radiate from the center, or the origin. So we say R is radial position. Okay, so that's something important to know about position vectors, and when you're trying to think about a y versus x graph, which is an actual two-dimensional picture of something's motion. Now, if I was to actually think about how an object moved, like maybe this drone or something, to go through these positions, it would have a path. And that path would look something, I don't know, maybe like this. In physics and in math, the letter that we use to discuss the path that the object actually went through is S. We use the letter S because it stands for space, and it literally stands for the space that you go through. You will recognize this because it's the same as arc length if you learned about arc length, or the amount of curve, or a specific amount of curve around a circle, which is probably something you learned when you did radians. Now, something interesting about velocity vectors at different positions is that velocity vectors are always perpendicular to the path. So if I was to draw the velocity vector here, the direction of the velocity would be perpendicular to the path. You know what, I should put arrows above all these. The same would be here. It's kind of just straight up touching it. I'm trying to do the best that I can. If it's a straight line, then the tangent is on it. Okay, so V is always perpendicular, which this sign right there, that means perpendicular to the path, which we could call S. Well, that's helpful when just trying to imagine what it is that's going on in some sort of physical situation. Being able to sketch a y versus x graph, though, what that requires is that you can use something called parametric equations. So parametric equations are a pair of equations that share the same parameter. And for us, our parametric equations are always going to be something with time. Time is our parameter. So maybe we have x is equal to 3t, and y is equal to, oh, I don't know, how about 9t squared? T is our parameter. And if we wanted, if we wanted to graph y versus x, not x versus t or y versus t, then what we would need to do is we would need to somehow solve this these parametric equations to get y equals blah 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 x. The best way to do that would probably be substitution. So like this one's really easy. I would say t equals x over 3, and then substitute that in. So I get y equals 9 times x over 3 squared, which would be 9 over 9 x squared, or just x squared. So if I wanted to graph this picture, it's just y equals x squared. Boom. Well, let's talk about how we would do that with the problem we just did. So here, my x equation and my y equation, if you remember, we said x equals 2t and y equals negative 6t squared plus 10. So if we wanted to sketch y versus x, what we would do is we would solve for t. So t is going to be x over 2. And then we would plug that in to our y equation, which would give us y equals negative 6, x over 2, the whole thing squared, plus 10, which is what? Negative 6 over 4, x squared, plus 10. So now I have a graphable equation, which I know is going to start at some position 10, and then have a frowny face kind of going down like this. Now if I wanted to draw the velocity and acceleration vector of the drone at 2 seconds, I would just look back at all of the information that I found at 2 seconds and say, okay, well my position is 4, negative 14. So we'll say that's maybe here. I don't know. The scale is wild. 4, negative 14 for the position. That would be the position vector, which we could draw like this. That's r. And then the velocity, whatever this path is starting to look like, the velocity is going to be tangent to it. So that would be the velocity. And the angle that it makes with the x-axis right here, that angle should be, if we look, about negative 74 degrees, which that means that it's going clockwise from positive x, and that is approximately what we have here, negative 74.1 degrees. For the acceleration vector, it just points straight down. So we would say that the acceleration vector is pointing straight down. Now, if this was kind of a more complicated x and y equation, then there's something I can do on my calculator. On my calculator, I can go to mode and change to not function, at least at the function normally, but parametric mode. Then when I go to y equals, it will ask me to enter an x equation and a y equation, which I can do here. Let's say 2t, and then what's this, negative 6t squared plus 10. Okay, great. So if I graph this, I get exactly what we were just looking at. So this is what you would use if you were asked to graph something that's a little bit more complicated, and like you weren't necessarily sure what to do with x and y. Of course, when you graph parametric equations, remember that your window, you need to set the t value. So this is the parameter, like how many times you're interested in looking at. And you almost always want to have a t step that's reasonable for the problem. So like for this, 0.1 is reasonable because by 2 seconds, you're already into the negative y components, and you're pretty far down, meaning this motion is happening rather quickly. You can always change that. If I did 1 and graphed it, now it looks a little lumpy. It's like here's 0, here's t equals 1, t equals 2, somewhere down there. Okay, great. So you can always use this parametric mode to graph when you have a y and an x equation that both depend on time. And of course, to set your mode back, you go to mode, function, and then boom, y equals your new equation. Okay. So yeah, fun stuff. You're really smart. This video is over. Congratulations.